Hello, my name is Ojis Chaudhary and I've worked on Design Assignment 3 and I've worked with my group members whose names are on the slide. Here's an image of our group. This assignment requires the development of a high current parallel plate supercapacitor for a satellite module. The capacitor is required to meet strict manufacturing space restrictions, and this capacitance is to maximize by varying the widths of its component with given constraints. The capacitor consists of a positive and negative plate and dielectric of specified thickness and a common specified length. The width of all components can be varied by a maximum of 4 cm for each component. The specific constraints include fixed lengths of 10 cm for all components, a maximum total width of 8 cm, and a maximum mass of 40 grams. To maximize capacitance, the plate or area needs to be maximized while minimizing the distance between the plates. I primarily focused on writing the Flex PD code and helping modify the code too. I also helped in writing the report and making the flowchart in the report. The aim of this problem is to determine the optimal component widths for the capacitor to achieve maximum capacitance while adhering to given constraints. The problem was solved using techniques typically used for electrical and magnetic applications, such as Gauss law for dielectric. A 2D model was created based on an existing 3D capacitor sample model from Flex documentations. The model was adapted to work in a 2D but was not able to accurately represent firing effects on all 4 sides of the capacitor, resulting in a slightly lower capacitance than the true value. To find capacitance, energy stored in the capacitor was used, and the Gauss law for dielectrics was employed to module the capacitor. Low conditions were applied to plates of the capacitor to simulate potential differences. The first validation method of the parallel plate capacitor module is calculating capacitance using E epsilon over E into ER into A over L. The maximum dimensions possibly yield 88.5 picofarads, while the simulation produces 90.4 picofarads. The small difference between the values can be explained by the fringing effects present on either side of the 2D module, which are not accounted for in the formula. The vector plot produced by the simulation illustrates these effects, therefore confirming the accuracy of the model. The contour plot of the voltage distribution in a capacitor with dielectric is consistent with the expectation, showing the voltage dropping throughout the dielectric from the negative to positive plate, and the sum of voltage spreading into the vacuum. The vector plot demonstrates the electric field in the straight across the dielectric, with highest intensity within it, and lower intensity near the edges of the capacitor. The fringing effect is captured by the module. The electric field appears toroidal outside the capacitor as expected. Moving on to the optimization, we modified to the existing code slightly as seen in the images here, where we export the data as text, and then we also change the input of the width of positive and negative and plates and dielectric material as highlighted in the blue image. Over here, we are inputting values and script in the string format method, and the numbers are in brackets shown in the index. This code is also an auto sweep. This has all the necessary functions to be able to sweep through the file data, organizing results, and run the files. Linear interpolation was not needed for this non-time dependent simulation. To determine the range of component widths, the constraints of a 40 gram total mass and maximum component width of 4 cm were taken into account, with lower limit of 1 mm. The code was made to sweep through every possible combination of values within this range, with a maximum of 7 data points. Rounding to within 1 mm was necessary to avoid n-grid errors in the Flex PD software. An extra check was added to prevent values exceeding 40 grams after rounding. The sweep range is initialized data is sweep, and multiple Flex PD scripts are run simultaneously. The capacitance is extracted from each output file and saved in a list along with the component widths. A 3D scatter plot is generated with component widths on the X, Y, and Z axes, and the capacitance plotted on the color map. The program breaks up data into chunks if more than 50 data points are present. So in this slide, we see our first iteration with the capacitance of 37.2 picofarads, with the given width of positive negative plates and the width of dielectric. On this slide, we see our second iteration with the capacitance of 43.71 picofarads, width of positive plate being 0.021, width of negative plate being 0.018, and dielectric width being 0.019 meters. Finally, our maximum output for our final iteration gives us 43.8 picofarads, with the positive, negative, and dielectric width being 0.019 meters. In summary, the task was to determine the optimal width of each component for a supercapacitor to maximize capacitance while adhering to strict manufacturing and space constraints, and to ensure the total mass of capacitance did not exceed 40 grams. The optimal width was found to be 1.9 centimeters for each component, resulting in capacitance of 43.8 picofarads. The value was obtained using FlexPD and Python and validated against theoretical expectations, while rounding limitations and other compromises had to be made in the simulation to be deemed usable with a reasonable degree of precision. Thank you.